Whenever we try to quantify anything in chemistry, we're working with a lot of particles, and that has to do with, well, really their size and how much is needed for them to be compacted together for us to be able to actually see them as a whole. And so, instead of spending literally a lifetime trying to count the single number of hydrogen or carbon atoms in something like your hand or an organ, etc., the chemists were trying to find out a new, more efficient way to quantify chemistry. So, Avogadro, whom it's often attributed to, did not actually create the number or the Avogadro constant. It was really just named after him in recognition of his work. In fact, there were many scientists or players involved when it came to determining the actual number that we use, called the Avogadro's constant. Now, all the several players into this development of the constant really had the same goal in mind, and that was to make quantifying large amounts of particles in chemistry and physics much easier and more practical. Now, the Italian chemist or physicist, depending on which textbook you're reading, Amedeo Avogadro, really laid out the theoretical framework in developing the Avogadro's constant. He figured out that regardless of the chemical and physical natures of a certain substance, at equal volumes, pressure, and temperature, you're going to have the same amount of molecules. Now, what is that ideal amount? Well, we have to set our lab conditions under ideal conditions. Really, we're talking about the ideal gas law, whereby the volume, temperature, and pressure are at a fixed ideal rate. While some of the notable scholars that were involved in the making of this Avogadro's constant, Einstein used Brownian motion of randomized gas particles to help develop this constant, as well as Millikan, in his famous charge of the electron experiment, was able to isolate the charge of a single electron, which was later on used to help develop this constant. In fact, one of the tools that they used, or frames of thought I should say, was that they looked at the charge of a mole's worth of electrons and found that when they took a mole's worth of electrons, added up that total charge, and then divided by the single charge of one electron, they got something extremely close to the Avogadro's constant that we have today. However, if we're looking to the first scientist to actually somewhat prove the existence or show the relationship of Avogadro's constant, we would have to look at the French physicist Jean Perrin, who through several experiments was able to actually prove the number of molecules in 16 grams of oxygen. Now, the number of particles as represented by Avogadro's constant was called the mole. And it wasn't called the mole because of someone's strange love towards that animal. It was called the mole because of a short form for the German word molecule to represent the amount of indivisible, or at the time, seemingly indivisible particles in that constant. So this triangle really sums up the relationships between the number of particles, the mole, and Avogadro's constant. And the way we read this triangle, like any of these helpful algebra or math triangles, is going to be similar in the sense that it describes the relationship between the three variables. If I were to place a circle like this over the variable that I want to solve, whatever's left over determines the formula for that variable that I have highlighted in turquoise. So we see that when I highlight the number of particles, it's equal to moles multiplied by 6.02 times 10 to the 23 particles per mole. Remember that 6.02 times 10 to the 23 particles is the constant for every mole of a substance. So if I write the mathematical formula for this, I would say that it's the number of particles equals the number of moles of gas, and I'll omit the E for short form, multiplied by 6.02 times 10 to the 23, where that is the Avogadro constant. Now, if I wanted to solve for the number of moles, and with that, I'll highlight that yellow. Well, just like in the previous formula, whatever's left over from that highlighted yellow is going to describe the formula to solve the highlighted variable. In this case, I have number of particles over 6.02 times 10 to the 23. Now in math, whenever something is above something, for example, like 2 over x, that fraction sign indicates division. So for this one, the moles of a substance are going to be the number of particles divided by the constant of 6.02 times 10 to the 23. The first example reads, how many particles are in 2.3 moles of hydrogen? Well, when we go back to our triangle, we can see that the number of particles is equal to the moles multiplied by 6.02 times 10 to the 23. So we're going to write here for particles, that's going to equal 2.3 moles multiplied by the constant of 6.02 times 10 to the 23, and that'll be particles per mole. And then what that does is, mathematically, the moles cancel out, and you're left with particles here. This gives us 1.4 times 10 to the 24 particles, where 1.4 was rounded because of significant digits. The second example reads, how many moles are in 1.24 times 10 to the 25 particles of Cl2? Now, if you notice, although we have a different compound here, or I should say gas substance, chlorine instead of hydrogen, the change in substance is not going to do anything, just like Avogadro concluded. So going back to the triangle, we're trying to find the number of moles. We can see that the number of moles is the number of particles divided by 6.02 times 10 to the 23. So we're going to write our formula here that the moles is going to be equal to 1.24 times 10 to the 25 particles over the Avogadro constant of 6.02 times 10 to the 23. This equals to an amount of 20.6 moles of chloride gas. Be sure to watch part 2 of this grams to moles and Avogadro's constant series, where in the next video we are going to show you more practical lab applications of this when we convert from grams to moles and moles to grams.